Well, today I'd like to talk about bipolar process flow. We talked about the bipolar transistor the last 2 or 3 lectures, and what was the big difference in properties between a MOS transistor and a bipolar transistor? What was the big difference in electrical properties between a MOS transistor and a bipolar transistor?
MOS transistor causes a current flow based on voltage.
Transconductive device, that's right. And a bipolar transistor?
Causes current gain from input.
So the MOS transistor is a square law device. It's transconductance characteristics primarily. Bipolar transistor is an exponential law device, but it's basically a current gain device. Bipolar transistor was the MOS transistor was conceived first. The bipolar transistor went into production first, and the MOS transistor now dominates many process flows. However, there are a lot of ICs that are still built today with the bipolar transistor, primarily because that exponential relationship between the controlling variable and the output is very attractive for many circuits. Okay. We had 2 models. We had a simplified multi-region model. This was a piecewise model, and it involved an exponential relationship between the base current and the base emitter voltage. Same exponential relationship for the collector current, although if we want to, we can replace that exponential relationship with IB in the model. And then we had some rather simple models in saturation and in cutoff for this device. And then we had a further simplification. We said oftentimes, if it doesn't make much difference whether the base emitter voltage is 0.6 or 0.7, we can replace it with this model here. Then we looked at one example. We looked at this circuit here. We don't have an input on this circuit right now. We're just looking at an operating point. And we analyzed the circuit. We guessed the region and analyzed the circuit and then verified. And we found out there was a certain output here. Then we changed the resistor on the base to a smaller value. We guessed and found out that if we guessed for it active, our verification failed. So then we guessed saturation and we found out what the output was. And then we looked at this structure here where we have a capacitor coupling a very small input signal. And we saw that when this input signal is small, this solution was the same as that first solution. We're going to see that's important a little bit later when we start talking about small signal amplifiers. This is actually a high gain amplifier circuit right here. And this calculation we just did determines the operating point of that amplifier. Okay. So let's talk about a bipolar process. This is very similar to the process flow that I talked about for the CMOS process, except now it's for a bipolar process rather than a CMOS process. And I'm going to work with a P substrate and an N epi layer on this process. This is typical for a bipolar process. Yes?
That came up in class homework. Why is it a P substrate? Can you also have an N substrate, or is that just how they decided to make the silicon?
We could also have an N substrate and a P epi. And in that case, the best device would be, if you take the same flow that we have here, the best device would be a PNP transistor. So we'll see in a bit why the flagship device we get in this process is an NPN transistor. Okay. Could be done either way, but if we did an N substrate, it would be leading to a PNP transistor. PNPs aren't as desirable as NPNs, primarily because of what?
Movement of holes isn't as fast as electrons.
The mobility of the holes is lower than the mobility of the electrons. Very much like analogous to the MOS process, where the P-channel transistor does not perform as well as the N-channel transistor in most aspects. So what we're going to look at here is the vertical NPN. That's the flagship device in this process. We'll look at everything else that's come along for a ride. So we build this vertical NPN and we get done, we say, oh, we've got a few other devices that are interesting. And those devices are a lateral PNP, a JFET, a diffused resistor, and a diode or a Bragg diode. I'm going to intentionally not make the features to scale, so that it's easier to depict where these different devices are at. One reason also is the vertical dimensions, much like in a MOS process, are much shallower than the lateral dimensions. Also, the processing equipment, most of it is the same that we use for MOS processes. So we can make feature sizes just about as small in a bipolar process as in a MOS process. In fact, you can go in the same front end, and with minor changes in the recipe, and by using one or two different pieces of equipment, you can change it from a MOS process to a bipolar process or vice versa. But we're also going to see that there are some fundamental differences in how we make the bipolar devices that will make the bipolar transistors much larger than the corresponding MOS devices. So here's our recipe. This is a process flow for a typical bipolar process. Mask 1, N plus buried layer. We don't even know what that is yet. Mask 2, isolation regions. Mask 3, pattern of the base regions. There's a mask in between I'm going to show if you want to turn some of the diffused regions into resistors. There's another mask that allows you to change the sheet resistance of that. Mask 4, emitter regions. Mask 5, contact openings. Mask 6, metal. And mask 7, pad openings. The number of masks here is really small. So these are pretty inexpensive processes. Okay. And very much like the MOS process, we have set of design rules. And here's the design rules for a typical bipolar process. And I've given the dimensions in terms of the parameter lambda. You can think of it as being a parameter like the parameter lambda we've been using for the MOS processes. And notice that the minimum widths and stuff, there are a lot of times around 2 lambda, which is similar to what we saw in the MOS processes. But I want to point out that something we didn't see in the MOS processes is some numbers here that are really big. We have a 24 lambda and a 14 lambda, a couple places, and a 12 lambda and a couple 6 lambdas. And it's these parameters, these design rules, that are what ultimately makes the bipolar transistor much larger than the MOS transistor. And we'll see why those parameters are so big after we talk about how the process goes together. Model parameters, the betas of the transistor. Beta forward is what we've been talking about. Beta reverse was corresponding to quadrant 3, where you rarely change the role of the collector and the emitter. And notice that beta reverse is around 1.5 in this process compared to beta forward of 100. It doesn't make a very good transistor if you change the roles of the collector and the emitter. Doping densities and so forth. Capacitances, just like we had for the MOS process, characterize each layer capacitance. Spice model parameters, and these may be Gummel-Poon model parameters. I'm not sure which set of parameters they are. Oh, and I want to point out one thing. The way we handle modeling the bipolar transistor is a little bit different than we handle the MOS transistor. With the MOS transistor, W and L have been entered for decades by the designers. You're going to find that the characteristics of the bipolar transistor are primarily determined by the area of the emitter. But we don't enter the area of the emitter directly. So what we do is, in a bipolar process, we model one transistor of a given dimension. So parameters are strongly area dependent are based upon an NPN emitter area of 390 square microns and a certain perimeter. So they give the character of that device. And then they give a scale factor. And the scale factor is how much bigger or smaller your transistor is than this reference transistor. So if your area is half as big, your emitter area is half as big, then your scale factor would be 0.5. If your emitter area is twice as big, your scale factor would be 2. Make sense? So instead of giving the emitter area directly, they give a scale factor. I'm not sure why it's evolved that way. So here's a top view of the process we're going to look at. And we will see what all these features are in a little bit. And this is how we looked at the CMOS process as well. Layer mappings. Gold will be N+ Berry collector. Red is going to be isolation diffusion. I guess brown was N+ Berry collector. Gold is P base. Green is N+ emitter. Contact is black. Metal is blue. And magenta is passivation opening. I'm not going to show the passivation openings here. That's for making bonding pads. We make them the same way we did in the lab for the MOS devices. So I'm going to look at the construction of the device, again, along two cross sections, AA prime, the upper part, and BB prime, the lower part. So we're going to look at top view and then two cross sections as we put this together. On the left here, we're going to see the vertical NPN transistor. On the lower right, we're going to see the lateral PNP transistor being formed. In the middle on the top, we're going to see an N-channel JFET. And a JFET has the same terminal designations as a MOSFET, a gate, drain, and a source. And it has length and width, much like the MOS transistor. The length is the distance between the drain and the source. And the width is the distance in the direction of the gate of the drain and source. There's a gate contact there. We're going to see that the model for a JFET is functionally identical, at least the simpler models, to that of a MOSFET. We'll talk about that a little bit later. Upper left is a diode, or a varactor diode, or capacitor. A lot of times we'll reverse bias the PN junction uses a capacitor. And on the upper right is a P-base resistor. Okay, so there's the device we're going to form. So let's first of all look at mask 1. And I've listed the mask numbers here so we don't have to go back to the recipe. I'll refer back to this periodically. So mask 1, first one is the N+ Berry collector. And it only appears in this part of the layout. So it's inside this region here and inside this region here. So cross-sectional view, we said we start with a P-type substrate. So that's yellow, lightly doped. Then we apply photoresist. And then I put the N+ Berry collector mask on. Well, actually it's a reticle, but I'm pretending it's a mask. So there will be openings then in this region here and this region here. Then I expose the photoresist. And when I expose the photoresist, the physical properties in the area that's exposed will change. Of course, only going to change on that lower cross section because that's the only place that the photoresist has been opened. And then I develop the photoresist. And develop photoresist removes the photoresist in the areas where the light had struck it. So now we end up with the P substrate exposed in those openings where that buried collector mask is at. And now we do an implant, and we're going to implant N-type impurities. Okay, of course the impurities get stuck in the photoresist, so the only place they actually make it into the substrate is in the area where that buried collector is going to be at. Okay. Then we strip the photoresist. Oh, you like that. And now we have our silicon surface again looking like P-type material, except in the areas where we put the buried collector at. Let's look at the top view of the same steps. So we start out with a P substrate. If you look down to the top, and after we put the photoresist on, expose it, develop it, and then remove it, we see the N+ buried collector in this region here and in this region here. Any questions so far? Hey, we're 6th done with this process because there's so few steps. Next thing we do is grow an epitaxial layer. What's an epitaxial layer? What's an epitaxial layer? Mr. Day.
It's a way that you're able to grow the substrate and have the same lattice structure and increase it.
Great. So it's a single crystal extension of the material underneath. So we make it thicker. And we're going to make the epitaxial layer N-type. And this is a thick epitaxial layer we put on. Okay. But one interesting property of an epitaxial layer, and it's a property that we want when we make this bipolar transistor, is that it can be easily uniformly doped. So if we implant and diffuse, we've got a gradient to the impurities. But if we grow it as an epitaxial layer, it's uniform. Okay, so let's grow epitaxy. There's silicon all over the place. Even though we have N+ buried collector, remember, we're only a few parts in a million or a few parts in a billion the impurities in this region. So it still looks like single crystalline silicon here and above. There's just a few impurities in that region. Was it growing? Well, it's still growing. Well, it's still growing. I think we'll stop there. Okay, so we have an N-type epitaxial layer sitting on top of the substrate now. And this N+ layer is buried underneath the epitaxial layer. That's why it's called a buried layer. Okay. Notice on this drawing, I'm showing this. I don't know if you can see the contrast or not. I have this a lighter green than I had before. Notice that this buried collector has migrated farther down into the substrate now, and it's also encroached into that epitaxial layer we're building, or growing. As you grow, that epitaxial layer is pretty warm, so diffusion occurs. And that buried collector diffuses down, and it diffuses up into that epitaxial layer. Is that clear? Okay. So you can see there's a step up here and a step down here. Does it make any difference which way you turn that wafer, vertical or horizontal, as far as this diffusion takes place? Does gravity affect this diffusion? No, not in a big way at all. So it makes no difference which way you orient that wafer when you're doing this. Okay, so now we're looking at the top view. We're ready to put the epitaxial layer on. If we put an epitaxial layer on, everything should turn out N-type. So grow epitaxial layer. And I guess the top looks N-type now. I put the dashed regions down here because underneath, this is where that buried collector is at. Next thing is the second mask. And the second mask is going to be the isolation diffusion. And the isolation diffusion is going to be diffusion inside all of these red tracks. It's called an isolation diffusion because it's going to electrically isolate this region from this region, from this region, from this region, from this region. So we're going to form 5 electrically isolated regions now with this isolation diffusion. So here's mass 2. Here's the mask. Now, there's a photoresist that has to be applied and exposed and developed and eventually removed. I'm not going to show the photoresist steps. I'm just going to show what happens now after we put this isolation diffusion in. So here is the top and the cross-sectional view. And if you look at the isolation diffusion, we end up putting impurities in the areas where that red mask was open. And so we ended up with impurities in here, in here, in here, 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 okay? Those were all places where isolation diffusion went in. It's important to note that this isolation diffusion is really deep. It's really deep because this was a thick layer. And we have to go completely through that layer to provide electrical isolation. We don't want N-type material to be connected to M-type material, or you get conduction here in a short amount. So this is a P-type material in between. It provides insulation between N-type material here and N-type material here. Notice also it's trapezoidal shaped on my drawing. And that's because as it diffuses down, but it also diffuses out. So you may have a mask opening that's small, like this. But by the time it gets done diffusing, it's going to be much wider on the top than the opening was. Okay. Here's the top view. We put the isolation diffusion in. Remember, it started out all N-type now because we covered it with epitaxial layer. When we're done, we have these P-type diffusions all the way around these N-type regions. So now we see the electrical isolation is taking place. Any questions so far? We're about 40% done with the bipolar process flow. And all we put in so far is a buried collector and the isolation diffusion. Next thing we're going to do is the P-base diffusion. And you can see where the P-base diffusion mass is going to sit. Here, here, here. Again, I've dimmed the stuff around it that will come later. So we're going to see some P-base diffusion on the BB prime cross section from here to here. From here to here and from here. So we'll see 3 segments of P-base diffusion on the lower cross section. And we will see 1, 2, 3, 4, 5 on the upper cross section. So this is mask number 3. Here's the mask. Again, I'm not going to show the photoresist steps, but when we do this diffusion and pattern of photoresist, develop it, do the diffusion, we end up putting P-base material into here, into here, into here. That's the 3 on the bottom, and the 5 on top. 1, 2, 3, 4, 5. Notice those are darker yellow than the isolation diffusion. These are our more heavily doped regions. Notice also that this base diffusion does not go close to the epi diffusion. We have to be sure there's epi underneath this before we get down to that buried collector. In fact, no place do we go through that that epitaxial layer. This is in the epitaxial layer, on the top of the epitaxial layer. From a top view, we put the P-base diffusion in. We end up with P-base material shown here. We're about 60% done. Any questions so far? Next thing I do is the N plus emitter diffusion. Here we see where the N plus emitter diffusion sets. Notice also we're putting an emitter diffusion out to the side here of what's going to be the transistor. This is going to eventually be used to make contact to the collector. We make it here. We also put it outside here. So this is mask number 4. Here's what the mask looks like. Let's put those N plus emitter diffusions in. So we see the 3 places on the bottom, and we see 2 places on the top cross section. Top view. Here's where that N plus emitter diffusion goes in at. Any questions so far? We're about 80% done now. Oxidation. We have to do oxidation a lot in the MOS process because we use that to isolate devices. To essentially raise the threshold voltage. Here's where we want devices. Here, we isolate devices by what? We isolated devices by what in the bipolar process? In the MOS process, we isolate devices by growing a thick oxide layer that effectively raise the threshold voltage between devices. So there's no connection, electrical connection. How do we isolate devices here? Yes?
The isolation.
The isolation diffusion. So we did isolation diffusion to isolate devices here. In the MOS process, we did an oxidation step to isolate the devices. So we haven't had to put insulators on yet. Now we need to put oxidation on because we're going to put metal on. So now we put the insulator on so we can put metal interconnects in. And so we put a thick layer of oxide on top here. And on the top view, it's going to be pretty ugly now because we cover it with oxide. All we're going to see is the oxide from the top, right? Next thing we do is contacts. So that's the next mask. So that's mask number 5. And here's where the contact openings are going to be. And these contacts are going to allow us to make contact from metal that we put down to a layer underneath, much like in the MOS process. We're going to see 6 contacts going in the lower cross section. 1, 2, 3, 4, 5, 6. Up here, we're going to see 4 on the A prime cross section. There's some other contacts there, but we don't see them in the cross section that I'm drawing here. So let's make the contact openings now. So here's the contact openings. Top view, contact openings. And if you look down here, some places you see N-type material and some places you see P-type material underneath, depending on whether you were above epi or above P-base diffusion. And we're going to cover everything with metal and pattern the metal. So here's the metal mask. That's mask 6. Here's the features of the metal mask. I guess we're going to see 1, 2, 3, 4, 5, 6 pieces of metal on the bottom when we're done. And we're going to see 4 on the top view that we're looking at. Okay, so put the metal on. then pattern the metal. And this is what the cross-sectional view looks like. Top view, put metal on. Whoops. Everything disappears. Now we pattern the metal. I think I patterned the metal. Yeah, remove the metal areas you don't want it. And we see oxide where the metal is not at. Okay, and I'm not going to do the pad openings for bonding pads, same as from Moss process. Okay, so what do we have? Here's our flagship device. This is a vertical NPN transistor. It's called a vertical device because it stands vertically in this device. We can now see the purpose of the buried collector. It's a hassle to get access to the contacts of that vertical transistor. We don't have any way to make electrical contact underneath it. So what we did was we put this buried collector, which is a low resistance region. So when current flows from the base to the collector, it flows into this. Very low resistance flows laterally here, and then it goes out here. So this buried collector is for the purpose of getting access to the collector from the top without having a lot of collector resistance. Make sense? Okay, so the collector is really right at the bottom of the base region here. The emitter is right at the top of the base region here. Current flows from the emitter through the base to the collector, or the other way around. You can think of the current flowing from the collector to the emitter. But we want this resistance in the collector here to be small. For a good bipolar transistor, it's important that the base region be thin. So when you put this process together, this distance here will be small. The thinner this distance is, the higher the beta of the transistor will be. Okay. Lateral PNP is right here. We see a P and P diffusion area. Why is it called lateral? Why is it called lateral? It's going across. It lays laterally instead of vertically. So the properties of this device are worse than one on the left for two reasons. One reason it's worse is what? Mr. Day.
Not as worse.
One reason the PNP is worse is what?
It seems like the base is a lot larger.
Okay, that's one reason. This distance here is going to typically be much bigger than the vertical dimensions. What's the other reason?
I was going to say the distance.
Yeah, that's a key one.
Holes are slow.
Holes are slower than the electrons. So it gets a double whammy. We make it big. But remember, this came along for free. There were no additional processing steps, no additional mask steps that were needed to create this transistor. So it's got bad properties. Use it if you want, but recognize its properties are not great. Make sense? Okay, so there's that lateral PNP. Here's the JFET. Notice what happens here. As we change the voltage between, we tie these two together, and this become the gate. As we change the voltage from the gate to the source, we will change the thickness of that P base region, and we can make it thinner. In fact, we can pinch it off, much like for a MOSFET. So current will flow through this base region, and we will control the thickness by the voltage between the gate and source, much like we did for a MOSFET. Okay. Of course, the diode is just a PN junction off to the left here, and the resistor is just a diffused P base region. So this is the pads. I don't need to spend any time talking about that. We've done that in the laboratory. The emitter area is the only parameter that plays a major role in the IV characteristics device. So we don't really care how big the space region is from a performance viewpoint. We don't care how big the collector region is from a performance viewpoint. We just care what the size of this emitter region is. It's essentially surrounded by base, and the base is surrounded by collector. Notice also that the transistor, even though I'm not to scale here, the transistor is much smaller than the area for the transistor, because you have to have here's the emitter, the base has to surround the emitter, the collector has to surround the base, and the isolation diffusion has to surround everything. So you might have this small emitter, but a lot of area to make this transistor. I'm going to spend 2 minutes. Do we have 2 minutes yet? I'm going to spend 1.5 minutes comparing the size of a minimum-sized transistor in a MOS process and a bipolar process, assuming you have the same processing equipment. And that's where those parameters, those big parameters, 24 lambda and 14 lambda, come in. But we can go back and make a transistor, and here's the emitter of a transistor, and a contact in the middle. We'll make that minimum size. We have to surround it by a base region. We have to surround it by a collector region. And if you go back to the design rules, let me step ahead. I don't have the isolation diffusion around. Here we've got the whole transistor. So if you surround the emitter by a base, by a collector, by an isolation diffusion, you see it's 75 lambda by 48 lambda for a minimum size bipolar transistor. Finally, we can compare that to a minimum size MOS transistor. So here's the gate area of a MOS transistor. And this is the area that you might want to allocate to the layout of that device. And this is to scale laterally. So you can see this area is a lot less than the area of that bipolar transistor. The area ratio is approximately 20:1 for a minimum size MOS transistor compared to a minimum size bipolar transistor. Primarily because that isolation diffusion, that's the major contributor. That isolation diffusion is so deep, so it has to be really wide. Are there any questions? Yes?
What is the P-base? Is that poly?
The P-base? No. It's silicon.
Oh.
There's no poly here. It's all silicon, just doped silicon. Thank you.